Joe, thank you. We are kind of fortunate to have Rick here to start off our meeting. I think all of you can hear me.
Good.
Yep, good. Okay. Rick Stevens serves as an Associate Lab Director for the Computing, Environmental, and Life Sciences at Argonne National Laboratory. Rick is also a professor of the Computer Science Department at the University of Chicago. His research ranges a whole range, kind of does a whole lot of things. He's kind of one of the pioneers in high performance computing, and at this point, trying to get the exascale systems going across the country. And his interests right now are actually in the biological sciences, using AI to accelerate cancer research is one of his pet projects, I would say, and he loves talking about it. He is probably one of the few people who has actually figured out strategic thinking to a science. And for one, I'm always trying to figure out the flow chart when I start listening to him on strategy. So of relevance to this meeting is Rick is one of the leaders of AI for Science initiative that culminated in a AI for Science report for the DOE Office of Science, which is very well received. And it has been, a lot of people worked on it, and including Rick. Rick was one of the leaders of the whole initiative and thinking about it. Now he's thinking about how to make it into practical reality, working with Office of Science. So I asked, I kind of requested him to share some of his thoughts on where he sees this going. So I welcome Rick, and I'm kind of going to give you an alert about 25 minutes into your talk, so you have 5 minutes left.
Okay.
I hope that's fine. Yep.
All right, great. So let me fire up this sharing here. I'm trying to make it big here. All right, thanks, Raul. Let me I've got a lot of stuff I want to throw out, and I'll try to. I'm going to go fast, and I can happy to make the deck available for people that want to peruse it later. All right, so a little bit. Just to motivate why we're doing this and where the kind of broader high-level strategic thinking is, it's useful to talk a little bit about the international AI landscape. So I'd say the big push recently started around 2017 when the Chinese put out a national plan for AI leadership, where they claimed they wanted to be the world leader in AI by 2030. And around that same time, Putin started tweeting about this and saying that whoever leads in AI will rule the world. And this of course, activated lots of people. The Chinese are planning to spend around $30 billion to achieve this leadership position. And, as of, last year or so, US non-defense AI spending maybe was approaching kind of $2 billion a year. So there's a huge gap between what the Chinese are willing to spend, I think, and what we might need to do. And that's kind of motivated the getting a plan together on the DOE side. So, of course, what's motivating this in the large sense beyond science is the fact that the belief that AI is going to contribute a massive amount to the global economic output of the country, of the world, and represents maybe a $13 trillion kind of market value by 2030. So that's got not just scientists, but the whole kind of system activated. And lots of countries have developed AI strategies, including the US. And the US strategy document, the first version of that came out in 2019, and it called for launching kind of a all-of-government type approach to a national strategy, and including like-minded international partners. And the Office of Science, AI for Science strategy development kind of is aligned with this. So, and of course, in the last year or so, year and a half, there's been other proposals made, one from some academics calling for a national AI vision. Schumer proposed a $100 billion proposal to boost AI funding, and so on. So there's, in discussion, something about a very large amount of money, say 120 billion over 10 years. That would be 4 to 5 times as much money as we're currently spending on that. So of course, at Argonne, I originally came to the lab to work on AI not in the 60s. I was born in 1960, but I came in the 80s to work on this. And the labs have had various activities in this. At Argonne, anyway, it started in the 1960s with Alan Robinson's work, who spent his summers there and then built a whole team led by Larry Wass, and Ian Foster was part of this group with me, and Russ Overbeek and Rusty Lusk and many others. and it really focused on AI applied to mathematics. And the focus that we had at that time was in symbolic AI. Of course, what's been happening recently, of course, is a huge upswing in connectionist-based AI. There's AI based around ideas of like neural networks. And three things have really driven this progress, right? One is that there was on the shelf a set of good methods, backpropagation, SGD, ideas for things like convolutional neural networks and so on. So ideas and methods are kind of sitting around. And then starting around 2007, 2008, there was an effort to build very large-scale training data sets, particularly ImageNet is the one that I think has probably had the most impact early on. And then at the same time, GPUs and affordable computing started happening. And so you had this kind of perfect storm. ImageNet gave us some large training sets of millions of images. And deep neural networks had gotten to the point where they started to work, and they representation learning that was replacing traditional methods of computer vision worked. And of course, since the ImageNet days, we've seen great progress, particularly in language models. So machines can score better than people in the Stanford reading comprehension tests. They're starting to do quite well, getting A's in 8th grade science tests, and soon in soon in the SAT tests. And there's a whole list of deep learning accomplishments, and some of these are bleeding over into science. Like, for example, DeepMind's efforts in addressing protein folding and many other areas. I've pulled three that I think are particularly relevant to what we think about. I'll throw them up here. So one is that there's been progress made in applying deep learning, particularly language-like models, to doing symbolic mathematics. So there's this great effort at Facebook AI Research teaching these systems to do solving complex integrals by using essentially systems that can do symbolic math to generate massive amounts of training data, and they show that the systems could generalize beyond the training data that they learn. So that's kind of cool. Another one is also coming from Facebook. It's a different group there. Has been working on unsupervised machine translation models for code translation. So it's a system called Transcoder, and it can translate from C++ to Java, from Python to C++. There's a nice paper up on the archive, and they're getting some pretty interesting results. And it's using a technique called sequence to sequence, which is basically also treating it kind of like a language problem, it's kind of a structured language problem. So that one's been quite interesting. And the third example is one applying artificial neural networks to the problem of the three-body problem, and showing that by combining their traditional method, their ODE method, to generate massive amounts of training data, using the artificial neural network in an ensemble with that system can not only solve the problem, but in some cases was getting a 10 million factor speed up, which is kind of mind-blowing. So one question we might ask is why are we talking about this in the context of exascale computing? And so it's interesting to ask the question, how much computing do state-of-the-art AI efforts need? So many people you remember the AlphaGo competition where DeepMind beat Lisa et al. And demonstrated kind of the first time mastery of Go at a very high level. And then very soon after that, there was a new version of this program called AlphaGo Zero that did learning and learned how to play Go by itself, essentially. It knew the rules, but it was just playing games. It basically played itself. And to train AlphaGo Zero required a couple of exaflop days. And I think that's one of the signatures of systems that are kind of state-of-the-art, that they require massive amounts of computing. If you were to replicate that study using commercial access to something like the Google tensor processing units, it would have cost about $30 million to actually train that system. So that's an example of a very large scale, very successful project, but something at the extreme scale of training, and is symptomatic of these very large scale efforts. More recent ones in language processing, there's a model that has gained some notoriety called GPT-3 that was trained by a combination of Microsoft and OpenAI team. It's one of the larger models at 175 billion parameters. And there's some concern about, who has access to computing to solve these kinds of models. And the current estimate is that model took around $10 million worth of computing time to train it. So both in game playing and in languages, some of the state-of-the-art models are very large and require very large-scale systems. Fortunately, DOE is going to have large-scale systems. So the 3 exascale systems that are on the Launchpad, Aurora, Frontier, and El Cap will have great combinations of CPUs and GPUs and will be perfect systems for large-scale AI training and for combined applications that take AI and HPC together. And Intel's, of course, pushing this concept that the processors, the new types of GPUs that they're making, will bring exascale for everybody, right? It's the same processor that we're going to use in our system. There's also a big push in startups building customized AI accelerators. We were one of the first customers for the Cerebras CS1, which has got the largest chip ever made, about 1.2 trillion transistors. It's very massive, it's about 8-inch square. And they were targeting performance in training AI models of up to 1,000 times GPUs. And we've had this system for over a year, and we validated speed ups up to kind of 300x and beyond on some of our first work in cancer. But there's a lot of companies making hardware aiming at these AI accelerated opportunities, and we're standing up a test bed at Argonne that will be available to the broad community to actually shake these down. And we've got hardware in there from Samba Nova, from Cerebras, from Grok, and from GraphCore, and others are coming. So let me talk about the AI for Science town hall process and where we are with that. So back in the summer of 2019, seems like a long time ago, pre-COVID. We could pack in. We had these 3 town hall meetings, and there were 3 meetings at the labs and then 1 in Washington, D.C. A total of over 1,300 scientists participated. And we looked at AI opportunities across the portfolio of science areas: biology, chemistry, materials, climate, cosmology, fundamental physics, energy research. We looked at the math foundations. We looked at ways in which AI could drive the data lifecycle, what kind of software infrastructure we would need to do a large-scale effort, what kind of hardware might be suitable for the scientific problems, and how we might integrate with scientific facilities. And so that resulted in this very large, about, 300-page report that came out in February of 2020. It's up on the web. You can Google for it. I want to thank Valerie and Arth and Barney and Jeff and Kathy and David, who were just, everybody was super helpful, and all people, including many of you on the call. And then earlier this year, the ASCAC subcommittee was formed to weigh in on AI for Science, and Tony Hay led that, and there were a ton of meetings in the spring. That resulted in a report, which I'll summarize here in a second. I'm just pulling out some areas. There's lots of opportunity in materials and chemistry, particularly AI-guided synthesis, and acceleration of codes in climate and biology, which you guys are all going to talk about. I don't need to tell you so much about what the opportunities are, but ranging from accelerating models to integrating data to changing, fundamentally how we process large-scale data, also in biology and physics and so on. One of the big areas is this idea of coupling AI and high-performance computing. So you can use AI to steer simulations, to choose parameterizations. You can embed simulation into machine learning models to do things where the simulation is kind of a teacher element. You can customize kernels, you can build surrogate models. All these things are very relevant to climate and Earth systems modeling. Of course, I don't have time to talk about them in detail, but there's 3 bullets that I think are really critical that you might want to think about in your workshop. So one is this idea of using simulation to drive deep reinforcement learning. This is it may take a little bit to think about this in the context of climate, but this is being used quite successfully to train control systems for autonomous vehicles, for aircraft, robotic systems, marine, and so on. And this is where you create a simulation environment, actually like a gymnasium, where the reinforcement learning system basically is controlling things. And there's many scenarios where you can use that. Second one is surrogates, where you replace internal functions with machine learned kernels. And this is being applied across the space in many areas. I'll say more about that in a minute. And then a third area, which may also be relevant for climate, is where you augment PD simulations with deep learning. So you introduce some machine learned terms that approximate the unknown component in the physics models. This may be particularly interesting in the context of processes that we have less understanding, biological processes or chemical processes, for example. So I mentioned the AI for Science report from the subcommittee that Tony Hay was working on. So this is a nice summary of it. There were kind of 4 main findings. This convergence of AI, data, HPC provides this big opportunity to accelerate scientific discovery. So that's the big opportunity one. Second point is that science can benefit from AI methods, and while industry is investing a lot in AI, the methods industry is investing in are unlikely to be sufficient to address all the needs in science because we have different types of data, we have different kinds of problems than industry. Third one is that the AI for Science promulgation, in some sense, through the Office of Science portfolio will enable US scientists to take advantages of these new capabilities in the user facility. So if you rephrase that, if we deploy AI and integrate it in the infrastructure, then it enhances all of our facilities and that'll enhance the science. And then this last one saying that we've got to create kind of a coherent ecosystem that ties everything together. So they recommend in this a 10-year AI for Science initiative, loosely modeled after the Exascale program. The structure of this initiative, I'll mention here in a second. Included in that is this instrument to edge initiative, which has a component that fits into things, experimental facilities like light sources and so on, but also could fit into facilities like ARM. A lot of training and retention work on the AI workforce, select interagency collaborations and international collaborations. So what would this look like programmatically? Well, of course, this is still all being worked out, but one rough idea is that it would be structured kind of like Exascale. So there'd be a focus on AI applications across the science domains, a focus on AI software and infrastructure that would support these applications and enable broad adoption of AI methods across the lab complex. Investment in foundations. This is what really didn't exist in the context of Exascale, but in the math and algorithms and general AI capabilities needed to support applications in science, investment in uncertainty quantification, explainability, and things like that. And then continuing push on hardware to support the vast computing needs needed for training such models. There was even a sketch in the report about how this might all tie together over 10 years. This is still very much a cartoon, but showing that there'd be some research phases, and then maybe it would transition into some kind of a big DOE project phase with milestones and so on about getting AI capabilities built in very specific fields. So at the end, what do we expect all of this to do? Well, an acceleration of discovery rates. So that's how fast we can create new knowledge across the space. We know in spaces like drug design, where we've been working on this in the context of, say, the COVID effort, that we were able to achieve over a 5x improvement in the rate at which we could quickly identify new molecules. The surrogate component of the AI is running about 50,000 times faster than our physics-based models, but by the time we put all the human and experimental stuff in there, we achieve an overall improvement maybe of like 5x. So that would be even great if we could get 2x in many areas. We think that this idea of moving from simple automation to much more goal-directed systems, kind of self-driving labs is an idea that we're quite interested in, or active learning loops where the system helps us decide what new data to acquire. There's a whole range of opportunities around these kind of new simulation AI hybrid codes that because of the performance of surrogates, getting in some cases factors of thousands, in our case factor 50,000 acceleration, means that an exascale machine now becomes something like a zetascale or beyond. So achieving deep integration of AI with simulation is going to be a grand challenge. How to do that with preserving reliability and accuracy and confidence is one of the key directions. We also think that AI will help us build accessible and integrated knowledge bases. We have to do that to acquire training data and to organize it, but AI itself can help us with making these databases much more accessible and easier to access from people that are not experts. And then finally, there's big opportunities in improving the infrastructure with all of this. So that's kind of what's happening. I'm happy to answer a few questions until Raul kicks me off. So let me stop the share here.
You have quite a bit of time. So any questions, guys?
Yeah, sorry about the audio. I'm visiting my daughter in upstate New York, or in Catskills in New York, with not the.
It's cutting off once in a while, but it was not too bad.
Okay.
Hi, I have a question. Hi, Rick.
Sure.
Nice talk. So do you have a sense for what the best way that AI techniques can sort of infiltrate a domain? I mean, I see it happening in sort of earth sciences, but I still feel like there's a whole ton of sort of domain expertise and knowledge that is not engaged with these methods.
Well, yeah, I certainly agree with that. I think what we need to pick is carefully identified problems where we have enough data, where we have a clear objective, where machine learning or some powerful technique could have impact, and do a number of these joint projects, where the AI people and the domain people are kind of working hand in hand. That's what's needed. Just to get enough of these exemplars kind of scattered, that people can see that it works and what is needed. And I think it's really important for people to understand that there's no free lunch here. I mean, I'm not talking about the no free lunch theorem in AI, which of course is another thing we could talk about, but I'm talking about the idea that you've got to have the data and you've got to have well-formulated problems. And we have to be able to relate it to some technology that we have, in some sense, already working. I'm not saying that there isn't going to be new AI methods developed. There is, but those have a longer gestation period. And so if you're trying to get the community on board in the short term, the idea is you've got to kind of show them where it works, and that's going to mean using primarily existing methods, tuned up, of course. But that's what I think has to happen. Now, you got to stay as much on the real axis as we can, but also keep people's attention focused a bit on the future. That even if half of what I'm talking about starts to happen, it's going to change how it's done. And those people who aren't part of this revolution could get left behind. So there's a need to encourage people to get their hands dirty, I think.
Just a thing to everyone. If you have questions, you can put in the chat. So Rick, here is a question in the chat room. They're asking, you mentioned some training for AI ML workforce. How should we do that practically? How can I get there? If there is an AI people mailing list, how can we connect efficiently? Are there dollars connected to that?
Yeah, so of course, each lab has got some activities going on, and I don't know where people are from. And one of the difficulties of doing all this remotely is you don't have a sense of the room and where people are from. Can't see anybody's name badges or anything. But many of the labs are organizing themselves around AI. Certainly at Argonne, we've got a bunch of mailing lists. We're doing this. We've been running internal town hall meetings and tutorials and training. I think DOE is going to have to step up and do some of that more broadly. The number of the companies that are selling, gear have kind of roadshow tutorials. I know NVIDIA is doing this. I know others are doing it. So there's mechanisms to bootstrap. Of course, there's things like Coursera courses and university courses. But I think each domain probably needs to organize a bit of of a curriculum, like what is it in, you know, in earth science or in climate or atmospheric science that people need to know about machine learning and AI, where it works, where it might not work, what are the open questions, what are the experiments people are doing, what are the methods that you need to learn, and then do some teach-ins. I mean, this is very much a dynamic bootstrapping process, I think. I think Oscar is going to try to take some leadership to do this, but I think each domain is going to have to do some bootstrapping as well.
So I heard Chandra has a question, but I'm not sure you can.
Well, I was busy typing it in. Can I just ask?
Yes, please, go ahead.
So I'm getting a overdose of AI here. On Friday evening at 5 o'clock, we had a campus-wide talk by Dan Jacobson from Oak Ridge.
Yep.
And he runs a big biology team. And then he showed the discoveries in COVID-19 that was possible primarily because of this exascale computing AI and et cetera, et cetera. But the main thing he brought together was the concept of system thinking as opposed to hypothesis testing that was driving science, whereas system level thinking that it brings in data and then describing things as a system and exploration. He sort of emphasized that, and then from a biology perspective, and then they said that's why we have gone from simple biology to systems biology. So I was just wondering if you could throw a similar analog or construct to earth sciences, atmospheric sciences, and so on, relating to AI.
Well, I certainly think that a systems view is important. And, you know, in biology, there's so many things that we don't understand about how biological systems work that we're in the middle of this, you know, 100,000-year mission to figure out how biology works, and to the degree at which we can represent open questions in systems biology and we have the data to train models that help us answer them, I think that's one way forward. I think in climate, it's a bit different. I mean, we have very successful models in atmospheric science and in climate that are not, I would argue, system models so much. And there's many things that we can do with those that the biology community doesn't have, right? So there's a focus, it's a pretty different focus there. In the cases of process models in climate, I think that's more similar to the biological systems biology kinds of frameworks. Of course, they have things like genomics data, which climate doesn't have, right? We have the ability to deep dive in a very narrow way in biology, and we can build on inference and learning on that data type. I think in climate, of course, you have something that we don't have in biology. You've got remote sensing data, you've got high volume instruments, and so on. So, I mean, I don't think you can draw a very direct parallel, but I think that you do need data. AI is not a magic wand. And we know from the language models that the more data, the better. We can, with deep learning, we can expand the scope of a model to be almost arbitrarily large, which means it can absorb almost arbitrary amounts of data. And as long as you've got the right structure, it can keep getting better as it gets exposed to more data. So that's a thing that I think is really important to get one's head around. Now, there was a question here in the chat I wanted to address. It said, you noted that first applications of science problems probably done with AI methods are well established, but these are uninteresting to AI researchers. Well, that's true, but this is the same thing is true in almost everything that happens in science, right? So you've got to start somewhere, and what's needed right now is enough demonstrations that things work, that the community can get itself oriented around the types of problems that are likely to work and stay away from the type of problems that are not likely to work, so you avoid wasting time early on. And that means that leveraging what, for example, in image processing. I mean, some of the work that was done last year on the Gordon Bell on the Summit machine was looking at cloud identification and cloud typing. I know some other projects working on that similar thing. And these are leveraging computer vision techniques at the heart of it, but they're expanded, right, to have more channels, to have different features where you have a multi-scale and so on, so that you're leveraging the progress in computer vision, but you're not just copying it directly. And I think things like that are really important to get going now. Now, ultimately, there's going to be methods that are specific to the domains. But I think you've got to build a community that is quite comfortable with the talking about the methods and working with them to be able to actually engage with the AI experts if your ultimate goal is pushing the development of new AI methods.
So there are two questions on the question chat. One is from Yolanda. It says, are the training data mainly for climate models? Are there enough observation to train these algorithms? And the second one from Lee is, could you please comment on the development of quantum AI?
Yeah, so quantum's easier. I'll take that one first. So, AI fundamentally is about data. And until we have quantum computers that are able to, and quantum memories, where we can actually load up classical data that is non-entangled data into some kind of internal quantum state that we can compute on it, we can't really effectively use quantum computers on AI problems in the near future. So it may ultimately be something, but I don't believe that's going to happen in the next 5 to 10 years until we have systems, quantum memories, and can handle large amounts of data in quantum computers. With respect to climate, climate models certainly can produce large amounts of data. And using that data for training, people are experimenting with that. I think you're not data limited in an internal kind of cores of climate. I think where you might be data limited is in process model development, where you need, say in biological interactions or something like that, where you're going to need high throughput experiments or some way of getting enough data. What we see in our biological work is that the deep learning methods start to become pretty effective at around 100,000 samples. And by the time you've got millions of samples, you're in a good place. If you've got thousands of samples or hundreds of samples, you're still in traditional statistics, is where you're, or maybe traditional machine learning. So that's just a ballpark, but it gives you some sense of that.
So Jeff Ster, our program manager, is asking, how do we retain people for science if they get lured immediately away by industry by 2x more money?
Well, of course, that's not specific to climate. I think you got to give them permission to work on the most interesting, coolest problems and access to the coolest hardware. And, and the people that stay are the ones you want. I mean, I don't know any way to fix that problem. I mean, industry can always dangle lots of money, but, I don't think a lot of people that are on this call want to make their living selling better advertisements on Google or better Facebook recommendation pages, right? That's what you're going to work on if you go to industry. So you can make more money, but you're selling advertising. So let's figure out how climate works and use the world's biggest computers and the coolest data streams. That's what this is about.
So there's one last question from Susanna Burrows, and she asks, so some of these first applications in science will probably be done with AI methods that are well established in practice. What is the funding mechanism getting started on these things? Because these are not very interesting to AI experts, for example.
Well, the funding is going to have to come from the domain sources. Don't expect the funding for AI in domain X to come from the computer science community. They've got tons of stuff to do, right? We've got to work with our program offices, right? The climate programs need to invest in AI for climate. Biology programs need to invest in AI for biology, and so on. You'll get bleed over, right? Those methods development, algorithms and stuff will come from the general investments, but no, each field is going to have to make investments. Now it needs to be coordinated, labs will try to bootstrap this, with internal money, but we have to really make, like in the Exascale program, there were substantial investments made kind of in the applications by the domains or under the guidance of the domains. And I think that's similar to here.
We have one more question. We have 1 more minute. And the question is, can you compare the computing capacity of private industry versus government?
Yeah, so the biggest kind of computing capability that we know about in private industry are, the clouds at Amazon and Google and Microsoft. And they've occasionally benchmarked them in a way that we can relate them to the kinds of machines in DOE. And they're not quite as large as the exascale machines that we're talking about. So in the next couple of years, the DOE will have as single systems that you could train coherently on the biggest machines. But they're of the same order of magnitude. And so, you know, the point that was being made in this OpenAI article that I quoted a little bit is that the institutions that will be able to do state-of-the-art AI systems need to have access to state-of-the-art computing. And that means most universities, of course, don't have that internal access. DOE will have machines that are state-of-the-art, and the cloud companies will have machines state-of-the-art, and a handful of other companies, maybe financial services, a few others, and that's it. And so unless you expect Google, Microsoft, and Amazon to do all the work for us, which I don't expect them to do, we're going to have to devise how to use AI in science ourselves. It's not going to come for free from Google. Fortunately, we've had the Exascale Computing Initiative, and we'll have this great infrastructure. And for the next 10 years, we'll have to keep upgrading that infrastructure and make it available to the scientific community for not just simulation problems, but for problems involving simulation and AI and pure AI problems.
Rick, thank you. We have reached the 11:40 time. Thanks for talking to us. It was inspirational. And thank you.